So yeah, I will talk about the way we're doing data analytics and building a data system for the free electron laser, which is just down the road at SLAC. Up the road. You're right, it is up. Definitely up. I've ridden my bike up that road, and it is uphill, let me tell you, all the way. And the free electron laser is called the Linac Coherent Light Source, LCLS. And I run the data systems division there. And what we're doing is not so much innovative because of what we can do, but how we've put it together to adapt to the very wide variety of experiments that we see. So I'm going to give you a brief introduction of what LCLS is and what we do at laser light speed. And then I will go into the architecture of the data system and what the building blocks are. And then I'll go a little deeper into some of the cute kind of innovative things that we've done with the on-the-fly data reduction and pseudo real-time and data analysis.
And you're going to talk about the scale of things, I hope.
I hope so.
Okay.
To sufficient detail for this crowd, I'm not sure, but if you have any questions, you can ask. How about that? So the Linac Coherent Light Source uses the Linac at SLAC, which is a 2-mile-long linear accelerator that takes charged particles and accelerates them to near the speed of light. It was once upon a time used to do particle physics, to take electrons and positrons, accelerate them to near the speed of light, and then bash them together, form a bundle of energy. But nowadays, that sort of experiment has shifted elsewhere in the world, and we have retasked the linear accelerator to be a laser, an X-ray laser. So what we did is we used the last third of the Linac, shown here, and we have, cool lights, and we have create electrons there. We accelerate them to near the speed of light, 99.99996% the speed of light. And then we put them through an undulator, which is basically a series of magnets that wiggle the electrons back and forth to produce X-rays. And these X-rays are then delivered to end stations, to experimental end stations, in the near experimental hall, shown with the blue dot, and the far experimental hall, which is shown in peach, maybe. And so you can see that the scale of it is several kilometers long, between the generation of the electrons to the generation of the photons to the delivery to the experimental halls. There are about 10 different experimental hutches or instrument end stations along the beamline, and each one does a different kind of physics, and sometimes they do a different kind of physics every other week. So it's a very challenging environment to work in because you never know what you're going to get. So just a view of this 2-mile-long, I don't know if you've ever been inside of a 2-mile-long building, but it is pretty wild. This is the undulator hall. This is where we take the electrons, we stick them into these magnets, and we wiggle them back and forth, and there's a feedback process that bunches them together into a 50 femtosecond long pulse, so a very short, narrow pulse, and generates about 10 to the 12th photons inside that pulse. So imagine 10 to the 12th X-rays. They're coherent, which means they arrive at basically the same time. And what we use them for is to image things. We use them to take pictures of things at the atomic scale. We are basically a 2-mile-long atomic scale camera with a femtosecond shutter speed. So if you want the analogy or the elevator pitch, that's it. 2-mile-long atomic scale camera. So these X-rays are delivered to the LCLS instruments. There are currently 7 of them. There are plans for more. And they vary in the types of science that they do. There's atomic molecular optics, which usually involves some sort of gas injection of atomic, of some sort of gaseous thing. You hit it with an optical X-ray to excite these things and make them wiggle and move and vibrate in interesting ways, and then you shoot the X-ray laser at them and you take a picture of how they're vibrating. And you take that picture at time t equals 0 after you've lased them, time t equals 1 picosecond, 2 picosecond, 3, 4, 5, and so on, and you produce a movie. And using this method, you can resolve the structures of proteins, capture bonds breaking and forming, and get a picture of how things behave in electronic and magnetic fields with a precision much better than anything we have today. There's also a fun hutch all the way at the end of the line called MEC, which is called Matter in Extreme Conditions. They mean what they say. They have a very large laser, high energy laser, that's separate from the X-ray laser. I'm going to use the word laser a lot. I'm going to try to be very disciplined about defining what I mean. This particular laser has the capacity to blast this target sample and heat it up to very, very high energies, to very high temperatures and high pressures, to form plasmas that you can then image with the X-rays. So you can imagine what goes on inside of a gas giant, or, you know, wherever extreme states of matter exist, really. So, no, it's a single blast, and it takes a little while to recharge.
If you could repeat questions.
Oh, sorry, the question was if it was a continuous laser, and that it is not. That particular laser is a blast and then a few minutes to recharge. This is a picture of one of the imaging instruments. You can see from the amount of tinfoil and wires exactly the sort of physics that goes on here. I love it because it is fly by the seat of your pants physics. I haven't seen this in a long time. This is hand in your pocket, another hand on the oscilloscope, checking the high voltage kind of physics. And it's great because experimenters come in and they basically have 5 days. They're awarded beam time. They have a proposal. They're awarded beam time. They have 5 days with this X-ray laser, this 2-mile-long instrument, to get the data they need and get out. And so you can imagine, and it's not as though these end stations, these lovely tinfoil and wire-covered things, are static. They change. They change every week. Sometimes they change every day, sometimes within 10 minutes. So new cameras come in, old cameras come out, new digitizers are brought in. It changes. So the configuration, the amount of data, the type of data that I'm reading out changes at least weekly. At least weekly. You can have 2 to 3 of these running at a time. So this is a very dynamic schedule. The science covers the whole map of basic research. And you can imagine that the scientific signature for all of the science is different. So what I'm looking for, what I want to analyze, is different from day to day and week to week. One week I may be looking at, one speck on a blob here, and other weeks I'm looking for bright specks here, other times I'm looking at waveforms. So the science dictates the signature and the detector, and that is what I have to analyze. So I have to respond to these needs of the user. So here I have a spiffy movie of what we're actually doing. So before I started talking, somebody was asking about differences between synchrotrons and free electron lasers. So one of the things that makes the free electron laser stand out is its exceptional brightness. There are a lot of photons in that little 50 femtosecond pulse. And why is that important? Synchrotrons can also take images of crystals. You take a crystal, you put it in the beam, and then you shoot your X-rays at it. But there aren't nearly enough photons. There aren't nearly enough X-rays to get a good picture of what's happening inside that crystal. Further, the crystals that you have to grow in order to image them have to be fairly large. LCLS does away with that. For LCLS, you do still often need crystals, but they can be very, very small. We call them nanocrystals because they're nanoscale, they're very small. And each pulse has enough photons in it to take a full image shortly before it destroys its sample. So what does it mean to have enough photons? How many are there? There are 10 to the 12th photons per bunch. Presently, they are arriving 120 times per second. We are concluding an upgrade now that will bring us to 1 million times per second. So 1 megahertz pulse rate, 1 microsecond between pulses, 50 femtosecond long, 10 to the 12th photons.
High energy, right?
High energy photons, yep.
How is this light all synchronized with the dropping protein?
Sometimes it is, sometimes it isn't. There's a timing system. So there's a timing system that sends signals down the beam line that can synchronize anything that's happening with the laser beam to within some jitter. And so there is the ability to trigger things to happen. With a lot of these sample injection, though, it's really just turning the pressure on a nozzle and going and letting it spray and hoping you hit something, which is great if you've got a lot of sample, but if you don't, then you really want to make sure your setup is just right before you put in your hard-to-grow sample and squirt it into the beam, because it's not a very well-controlled process right now. Yes?
Have you tried DNA samples?
Have I tried? I do not know the answer to that. I'll have to get back to you. I don't know if we've done any DNA. That's a good question. But the shot is this. This is the rough schematic of what's happening. The electron beam is that bright light coming in and heading towards that blue plate there. The green blob is our sample, our beloved sample that we're injecting into the stream. And we hope that the green blob and the light blob intersect and that it diffracts before it gets vaporized, and it diffracts onto that blue panel, which is a camera, typically some sort of CC or 1 to 2 megapixel camera that captures the light that's scattering off of the target. So these things are coming in at 120 hertz currently, and the data processing that's required in order to take this image, which really does look like that little speckle pattern there, deconvolve it and turn it into what is essentially a structure of a protein, takes a lot of computational power. It takes some time. Well, I can tell you, I will quantify exactly how much computing it requires using our current methods and current technology to reconstruct to something like that. The challenge that we have right now in our data system is that our data throughput is about to go up. So as I said, we are operating at 120 hertz, which means 120 times a second we get an X-ray pulse in. Again, an FEL is kind of unique in that, for the most part, each pulse is an experiment. Each pulse is a statistic. So every time I hit a sample, it's like a whole new experiment. And I have to figure out which bucket I have to put that experiment into later, after the fact in the analysis. But essentially, it's one full experiment. And so right now I get to do 120 experiments per second. And in a few months, we're going to turn on a new superconducting undulator, and we're going to be able to go at a megahertz. That's a lot. So for those of you not familiar with orders of magnitude, we calculated that our data throughput, the amount of data this isn't just the scale of the repetition rate, but the data throughput will go up by 3 orders of magnitude by 2025. It's going to take some time for the cameras to catch up to be able to run at close to that rate, but that's what we expect. This is by far SLAC's largest data challenge right now, and it's going to hit us in 2 months. So right now I'm very calm and relaxed and not freaked out at all. In 2 months' time, I'm going to be gray. It's going to be something else. So here's a picture of the nanocrystallography pipeline, which essentially is you take these nanocrystals, you put a stream of them, you hope they intersect with the X-ray beam, you capture the diffraction on that multi-pixel detector. What I want to call out in this slide and the next, so I pay attention to the green and the blue numbers. That's what's important. So for a multi-megapixel detector that's reading out at, say, 8 kilohertz, it'll produce about 60 gigabytes per second of raw data coming out. Now, if you look at that X-ray diffraction image, you will notice that there's not a lot there. Sometimes there is, and sometimes there isn't. Sometimes it's a blob in the middle of the screen, and sometimes it's this. So what we do is we have various techniques for figuring out whether or not this is interesting or not. This one actually is. And if it's not interesting, we throw it out. So we have a veto that looks at the image, looks at the event, and says, you know what? I don't think we had a hit. Our beam didn't intersect the sample. Throw it out. And so we remove it in real time. We don't write the data to disk, and we move on. So this red box that shows data reduction tells you how much computing is required in order to do that level of data reduction. And I show 2 time scales. One is 2024, that's an 8 kilohertz, 4 megapixel camera. By 2027, we think it's going to grow up and turn into a 16 megapixel camera and be able to run at 40 kilohertz. So by 2027, we expect we'll need 16 teraflops to handle the data reduction aspect of it. So this is great. This gets us a factor of 10 reduction, and now we're down to 6 gigabytes per second heading into disk. We write that to disk, and we start analyzing the data. We look for the peaks. We do the indexing. We orient the patterns. We put them into bins saying, you know, this one was facing this way, this one's facing this way, this one was facing that way. And then we average each bin, and from each of those we recover an intensity map, the electron density, and reconstruct that protein that's on the right. The amount of computing that this requires is of order 4 petaflops in 2024, and 20 by 2027. So it's a pretty big increase in the amount of computing that's required to do an experiment from today, where 50 teraflops has covered us for the last 10 years. And so we have to find some way of handling the challenge. But this isn't even our worst case. This is just our in-between case. There's single particle imaging. The setup is very similar, but in this case, we actually are taking individual particles, which could, for all I know, be DNA. They're macromolecules. They're fairly large proteins and things. And we drop them into the beam and image them. And same detector, same rate, but this time, and same data reduction, in fact. We do the same thing to reduce the data. But the data analysis on the right side is astonishing. And now it takes an exascale computer by 2027 to properly analyze this data in a way that doesn't take years, because it's running at 40 kilohertz, right? So we did the math and we got well and truly scared. And then we said, okay, but we can, if we work really hard, we can figure out a solution for SPI. And then somebody reminded us that we have other instruments and other types of science going on. And this is just 6 of them. We've actually identified over 20 typical experiments that can happen in any given year, with these being the sort of relevant examples. And from the left to the right, the numbers show by date, 20, when you expect to see a certain basic throughput. So that's coming out of the detector, that's the raw data. And then what you need to do for the data reduction in order to reduce it, how much computing do you need, and then finally how much you need for the analysis. So you can see that for coincidence spectroscopy, we have, this is happening in April, by the way, coincidence spectroscopy that we're doing will start out with a rate coming out of the detector of 200 gigabytes per second, which is challenging. But it only requires about teraflop to really analyze the data. So it's not hard to analyze. There are other things that are a lot harder to analyze. So we're all over the map. The point is, we're heterogeneous. There is no one solution that fits everything. So what did we do? We created a data system architecture where one solution fits everything. Let me explain why we're not idiots. So first we thought about what do the users need in order to do their experiment in 5 days and 4 months and a year? How do they get to the answer? Because in the end, we are a facility, we provide a service to users, we provide a beam and the ability to take data, and the users have to do the analysis. And they do the analysis on top of our hardware and software stack. And they have to be able to get their answer in a timely fashion. If we take data that they cannot analyze, we have wasted a lot of resources. So we took that seriously, and we wrote down what it was to be a user at LCLS and what they needed. And so the first thing we realized is that when you're on the beam line and you're actually trying to get things aligned, if you have a hard time getting if your jet is moving around like this, or if there are ice crystals forming on your sample jet, you can't get it to intersect the beam. So you need to have some camera looking at that jet. And you need to be able to adjust the pressure on the nozzle and then watch in real time to see whether or not that improved things. So we have this sort of 1 second human interaction time feedback that lets us actually see what's happening. We can move a motor or adjust a mirror or adjust the pressure on a nozzle and see in real time whether or not that has affected what we're seeing. The second layer of feedback that we need is some measure of data quality. So for that, you usually need something a little more sophisticated. So we have another computing layer behind the first one that gives us feedback of order a minute. And it actually looks at the data and runs an analysis and provides some measure of data quality. So it's the sort of thing where, are we getting enough statistics? What's the signal to noise? What's our hit rate? How many single hits do we have relative to multiple hits and things like that? Off shift, users have to be able to pass through the data multiple times. So we need a compute farm that's large enough to handle multiple jobs running concurrently 10 times a night. And usually about within 4 months of the experiment, they have published data. So we keep the data on disk for about 4 months. At that point, it becomes available. It's always migrated to tape. So we store it on tape for 10 years. 10 years on tape. You can restore it for a month after that 4-month period expires. So we try to be nice to the users and give them all the tools they can in order to be able to do their analysis. So here's what our data system looks like in schematic form. So the data flow is from left to right. On the left side is the detector, which is producing data of order 200 gigabytes per second in about 2 months, up to about terabyte per second within the next few years. And then in between there is a small, moderate, few teraflop compute farm we call the data reduction pipeline, which is the real innovative bit of what we're doing, I think, that dynamically reduces the data by a factor of 10. Factor of 10 is an eyeball. It's kind of sometimes you get better, sometimes worse, but about factor of 10 is what we need in order to be able to write it to the disk. I should say, and I should say at any point, you could scale your way out of this by throwing money at it. We could buy more computers. We could, distribute the file system over a larger number of nodes. It costs $250 million per year just to store the data. I think there are better things that we can do with our money than to pay for disk storage. So we've tried to go smarter, not throw money at it, not just scale our way out of it. But we do have certain bottlenecks within the system, and most of our solutions are crafted to avoid one of the bottlenecks. So we have our data reduction pipeline, which is also tied to a small processing farm that lets us do this 1-second monitoring, which is looking at a statistical subsample of the data streaming through, so that users can get a real-time feedback of the latest of what's happening. We have a data cache, that's the little green bucket there, that also has a processing farm attached to it that lets users get feedback of order a minute. And then on the right side, we have the other innovation. So we do have a mid-scale compute facility that we're building at SLAC. It's modest. It'll be a petaflop or so eventually, which is modest.
You could use more.
No, it's not all that modest.
It depends on your context.
Try to go buy yourself a Exascale machine today, you'll have a hard time.
Yes. So this is a future, sometime in 2024-ish is I think when we need that. But regardless, so we have a mid-scale compute farm at SLAC. But when we went to the DOE and we went, but we need an exascale compute farm in order to be able to handle our data, they said, no way, you can't have one. And so he said, fine, we'll take our toys and go somewhere else. We have NERSC right across the way, and they have an exascale computer. They're building one, right? We also have Oak Ridge on the other side of the country, and they also are building an exascale compute farm. We have Argonne. And so we said, all right, we'll skip some of this now. We'll go ahead and we will stream our data to one of these other places, and we'll analyze it there. That sounds great. And then you start looking at the details. So this is our second innovation, is how do you actually do this? How do you actually take data from a BES user facility and stream it willy-nilly across ESNet, which is a government-provided network facility, to one of the advanced and scientific computing research facilities that are out there? Turns out this is not a common use case. So we're breaking new ground here. So the key here, we use the data reduction so we can fit into these pipes, so we can write to disk, and so we can stream the data across ESNet, so we can fit it into that bandwidth so we can get to NERSC. That's the deal. Those are our bottlenecks. Writing to disk, ESNet. So those are our pressure points. So again, to reiterate, what to me are fairly scary numbers, your mileage may vary. Our detector output is of order 200 gigabytes per second up to a terabyte per second, and somehow we have to get it down. So with all of the tricks that I'm about to talk about, we get it down to the little blue line in the top plot, which is much more manageable. The integrated storage for all of that is shown in the bottom plot, also much more manageable now. So the discussion of the bottlenecks are basically that if writing it to disk and reading it is hard, it turns out. If you can't move the data out of SLAC and to a high-end compute facility, then you're stuck and you can't analyze your data. That is also bad. And if you reduce the amount of data you have to analyze, if you analyze it earlier, then you don't have to analyze it again later. And what is the first step that users do when they want to analyze their data? They get rid of all the junk. So people already use data reduction. We're just moving it up. We're doing it earlier. So that's not particularly innovative, but socially, that is a huge paradigm shift for this community. So what we're doing is more socially innovative than technically, But it's been a struggle to get general adoption. So it's been mandated by the facility. We are doing data reduction, and everybody is getting on board, and I can't wait to see it. I think it's going to actually make lives better in the end. So we did go through the diligent process of identifying all of our experiments, and we put them into a giant spreadsheet. I didn't show you all of the spreadsheet because it would make your eyes cross. So I only showed a part of it to prove that I did some of the work. So we identified all of the possible experiments that LCLS has done and we think will do. Again, this is a Gedanken experiment. So once we actually see what the new source can do, these may change. But for now, we were just trying to get an estimate of how much data storage we needed and how much throughput, how big we had to handle, how big the network had to be, and how much computing we needed. And so for each of these, we identified a method of data reduction with the target of about a factor of 10, but mostly we wanted it to fit within about that 20 gigabytes per second. And then we identified some way of getting data quality, some fast feedback measure, and then we identified what the analysis was actually going to be. And we ran all of these on candidate data sets, and we put them against a time axis, so that we said, okay, well, when we start up, we're going to start up with the soft X-ray, so these experiments will get all the time, and then later we'll introduce something new here, and that will get more time. And so we did the best estimate we could to show how much beam time they get. We folded in how much uptime experiments actually have historically, and we put it all together. And that's how I've generated the plots that I showed before. This one is the other plot produced by this exercise, which is how much computing do we need? So this plot shows computational requirements in what is not a linear scale. It's not even log. It's binned on the vertical column against time along the bottom axis. And the size of the bubble represents the percent of experiments that fall into that particular spot. So, for example, in 2021, we expect that 11% of experiments will require between 125 and 250 teraflops of analysis to run. And so we looked at that and we said, well, up to about a petaflop, that's not so bad. We could probably find a way to get smarter and manage that. But then you look up at the top and there are these things that are way up there, and you go, well, okay, we don't have years to analyze data, so what are we going to do? And so the answer was to take advantage of all of these other facilities that the DOE has given us. So they have high-end compute at Argonne, Oak Ridge, and at NERSC at Berkeley. And we have the ESNet network, which is a well-provisioned network, actually, that allows us to stream the data to anywhere it goes. It does have a connection to NERSC, so we picked that as the pathfinder. And we are planning on streaming those high compute requirement experiments over to NERSC to analyze. So, shifting gears back to data reduction. This is going into the nitty-gritty of what we're doing in order to make us be able to analyze things on the fly. So, I have this analogy. And the analogy is, fisherman goes out in his boat, old boat, but new net. And he catches more fish than he can carry. So what does he do? How does he handle this? He has some options. He can throw away the not fish. Get rid of the starfish, get rid of the boots, the plastic straws, the sea turtles, whatever it is that he caught in the net that is not a fish, gets thrown back. You can do feature extraction. Fillet the fish, get rid of the head, tail, scales, whatever, and just keep the fillet. You can go all sardine on it and squish it together and pack it as tight as you can without sinking the boat. As I'm sure you've concluded, this is a good analogy for what's happening at LCLS-II. We are collecting more data than we can effectively store. And so we need to come up with some data reduction methods. And these are the three basic ones that we have available to us. The trick is adapting them to the 20 different kinds of experiments that we have. So we've developed a toolbox of different techniques that can be parameterized to suit all of the experiments that we've identified. So we have compression, both lossless and lossy. Lossless gets you a factor of 2 to 4 at most because of entropy. Lossy could do a lot better though, but you have to be careful and make sure it doesn't affect your data result. feature extraction, we can do sparsification. If we only illuminate a blob in the center of the screen, we can just read out the blob. So it's not rocket science. You can do data transformation into a space where data are sparse, like JPEG style compression. We have our veto, which is essentially a software trigger that takes signals from all of the things contributing to a particular pulse, looking at the totality of the event and saying, you know what, there's nothing interesting here, just throw it all out. And we have multi-event reduction, where you can actually correlate things over events and combine them together. One important feature of this data reduction pipeline is that we are saving a programmable fraction of these events in both their reduced and non-reduced form. So raw data plus reduced data next to each other. We've picked about 100 hertz, which is an LCLS-I style data set. So one, if we screw it up, users will still leave with an LCLS-I style data set at the end of the day that they can analyze. And two, this gives us a tool to make sure to validate the data reduction and make sure we're not screwing it up in real time and later. So that's an important feature that anybody who does data reduction streaming like this should build into their system, is to make sure that you can validate it later. So I'll go into 3 specific examples of what we can do to reduce the data. The time tool, which is an FPGA processing, the Lossy compression, which is kind of gives an interesting result, and beam center determination. So the time tool, this is the one where I'm going to use the word laser a lot, so I will try to be precise. So the time tool is a diagnostic device. And as I said before, with some of these experiments, you have a target, a sample, and you pulse it with some optical laser. And this optical laser then excites it to some transient state, which then decays. And you'd like to be able to sample that state at fixed times from when you have pulsed it with the optical laser, and get statistics in each of those bins so you can see the time evolution and make a stop motion movie of what is happening. However, the X-ray laser is generated 2 kilometers away from the experiment. The optical laser is near the experiment. So there's some jitter. I mean, there's a timing system that tries to maintain sync. But in the end, there is some jitter in this. And so rather than trying to control that exactly, it's easier to just measure it and correct. So we measure it. So this time tool is what does that measurement for us. And it's kind of cute. So what we do is, at the same time as we generate that optical laser pulse, we also generate a little white light pulse. And we send it through this little screen with the red on it there. And before we do, we put it through a diffraction grating, through a slit that chirps it, that creates a rainbow. And so the blue stuff, the shorter wavelengths will arrive first. The longer wavelengths will arrive last. It's a few femtosecond long pulse, 50 femtoseconds or so long now. And we put it through this special screen, which we allow the X-rays to hit as well. And when the X-rays hit it, they change the index of refraction of that crystal, or of that screen. And they allow the light to pass through. So we look for an edge. And if we see blue, we know the X-ray laser arrived earlier. If we see red, we know it arrived later. So in this, we look for an edge. So basically, these images are the images of the 2D detector that we're using to image this screen. It's cute, isn't it? Mm-hmm. And we project it down to this 2D, to this projection. And then we just basically convolve the signal with a matched filter until we find that edge. And that's our time. So this we can do in FPGA. So we used to do it in real time in software and attach it to the data and just send out the result. We've moved it into FPGA because this is the sort of analysis that's stable over time, doesn't change, everybody uses it, and everybody uses it in the same way. The only thing you might have to change is the filter, the parameters on the filter. That's easy to do. So this is a very manageable thing and a good example of a case where you can develop something in software and CPU and move it into FPGA and save yourself a whole lot of effort transmitting data over a network. So that's the first example. The second example is lossy compression. And it's a special kind of lossy compression. It's called SZ compression with a region of interest. So we identify a region of interest that we want to be lossless compression, and the rest which we want to be lossy. And then SZ compression takes the stuff that's to be compressed, it bins it, and it applies a fixed error bound. And then it does the compression. And what's interesting about this, so a lot of times once you actually start looking at images like this, the detector reads out as a 2-byte, ADU. And we turn it, in order to get an actual image out of it, we have to correct it. We have to subtract noise, we have to do common mode and gain corrections. And that inflates the image. And so, because it turns it into a float, a 32-bit object now, and ultimately, this is what is fed into the SE compression algorithm to actually compress it. So what we did is we evaluated this. We had a data set of 4 million now selenium data, SAD data, and we identified these little peaks, these bright spots, as our regions of interest, and then applied SE compression to the whole thing, and we achieved a compression ratio of 21 over the input data set, which is really good. We compared the analysis with the original versus the compressed and found that, in fact, lossy compression gave a better result. This is shocking. This shouldn't be. What we realize, I think, is that in binning in the binning step, we probably denoised it. And that's probably why it gives a better result. But in fact, when we actually did the indexing and tried to find the hits, we found more in the uncompressed, in the compressed, uncompressed data set than in the other. So that was an interesting result. The last thing is sort of one of the common things that we do is sometimes in wide angle and small angle X-ray scattering, you end up with these rings. And what we need to do is we need to find the center and then at each radius integrate around the ring and project it down. Finding that center is the first step and is very challenging. If you can then integrate those rings and project them to a spectrum, then that's a lot smaller than this original data set. But finding that center is challenging. So we've developed a technique using Huff transforms with Canny and Ransack algorithms to find those circles. It works in a lot of these tricky cases, including the ones shown here. It still fails for faint or wide rings, or if we leave a beam stop in there that we haven't masked off, it's not smart enough to catch that we've done something silly. But in the majority of cases, it works quite well. So these are examples of the sort of data reduction that we're doing. So now I'm switching gears a little bit and moving to the other half of our sort of innovation, which is trying to stream data over to NERSC. And so there is a pilot project called Exascale, whose official title is Data Analytics at the Exascale for free electron lasers. And it's basically a pathfinder. It takes SPI nanocrystallography and tries to work out the entire workflow from beginning to end, from the data to analysis, including all of the infrastructure to stream the data across ESNet over to NERSC. It's taken several years to actually get there because it's a very difficult piece of work. Along with that comes porting our data analysis framework. So the user writes their own analysis script in Python on top of our software stack, but we have this analysis framework called PSANA, Photon Science Analysis Framework, that sits there, and it's the intermediary. So it accesses the data and it handles all of the parallelization. And what we do is we provide lots of common algorithms that people can string together to do their analysis. We provide corrected, calibrated data, handle several file formats, and provide tools for doing visualization. And we try and hide all of the complexity that's underneath, so that when a user runs on our local facility, it's the same, it looks the same, feels the same to them as running at NERSC. So running on hundreds of cores or thousands of cores should feel the same as running on hundreds of thousands of cores. This is not an easy thing to do. Add the complexity to that, in that we want to be able to stream the data, and actually we're not waiting for the run to end and for the data to be fully transferred before we start analyzing. We start analyzing as soon as data arrives. And so we're accepting data as it's coming in. So that adds a certain complexity to the whole process, because you have to make sure the data gets there and is properly distributed across the nodes to make sure that across the cores, so that the analysis engines can then crunch on it. So this is a really ambitious scaling exercise. One of the things that's helping us is to use Legion. The current version of PSANA uses MPI to do the parallelization, but there are some better ways of doing it, including this Legion software that's coming out of, or data model that's coming out of Stanford, that does a better job of overlapping I/O and compute, and hides the complexity of moving from an architecture of, say, CPUs to a GPU-based architecture. So it can handle heterogeneous architectures much more elegantly than MPI. MPI, the user's kind of on their own. They have to do the CUDA thing of moving. Data transport through all the layers of a memory hierarchy on a machine are costly and difficult, and Legion hides that. So we're pushing in that direction. So Legion provides this performance portable execution of tasks on multiple architectures, and PSANA does the tasking. It says, here's the data analysis you need to do. Here are the tasks that need to be done. And then Legion takes those tasks and distributes them on the architecture. In this way, we maximize the throughput of the data analysis, and we get asynchronous I/O and compute. So we don't have to wait for all of the data to arrive before we start chugging on it. And it gives us a lot of this performance portability because, like I said, if we want to run at NERSC, then we have to have a CPU-based architecture. If we want to run at Oak Ridge, we want GPU. So it just varies. So I will not talk about that in great detail. The sort of last detail of this is that ESNet is not just a series of tubes. It's not just wires connecting point A to point B. It's really much more than that. It's a software-defined network, and there are resources behind it, a network resource orchestrator that can, on the fly, dynamically figure out what kind of resources you need in order to handle a job so that you get consistent data transfer times. So if I'm streaming data at a terabit per second across this network, I want to be able to get a terabit per second consistently for the time that I'm running, and not sometimes 100 gigabit and sometimes maybe more than a terabit, whatever. So there is this sort of dynamic network resource orchestrator that can talk to the actual analysis, figure out what's needed, and then provision the resources inside the software-defined network properly so that we can get consistent data transfer between LCLS and some other space. So I think I'm going to leave it there. I could say more. If you have questions, I would love to answer them. But I will say that from my perspective, this is a big challenge. And the challenge covers throughput, real-time analysis, storage, and computation. What we have is a modular architecture where we have a single analysis framework that can run at all three layers of our compute system. And we have the ability to take analyses that are developed in, say, the offline processing and move them closer to the detector and possibly into the detector itself. We have the ability to provide feedback to the users at second and minute timescales. Even better than that, there are a few places where if you actually move stuff into the hardware, if you actually move some of the analysis into the hardware, you can have hardware signaling back to detectors or to the timing system at the level of tens of microseconds. So now sub-millisecond signaling to say whether to accept or veto an event is now possible. And it's dynamic. That's the thing, is it's different for every experiment, and every week we get a different one. We paired that with some analysis and visualization tools that let people view things in real time. And we try to make it as easy to use as possible because although we have some users who come in very large groups who have the ability to mount a very large computational challenge to solve their problem, not all groups do. There are some very small groups, and for them they want a laptop and MATLAB. And I can't give them a petabyte file and say, lots of luck, right? So it has to be easy enough for the breadth of users to use. I think we've done that. So I think with that I will conclude, and I'm happy to take questions if there are any.
What GPUs are you using?
That's a good question. Titan was what we were using, but
Well, since using FPGAs, some GPUs
yeah.
use FPGAs,
So
you could use those to do some of your FPGA work.
yeah, we haven't. So
But
We
it's a
have,
longer discussion.
it is a longer discussion. I will say, so at the beginning, the sorts of experiments that we're doing don't involve imaging detectors. There's a reason I don't have a good answer for you, and that is because we're taking a wait-and-see approach. So mostly what we're doing is stuff that needs flexibility more than it needs image crunching. And for that, you want CPU. And so what we've gone with right now is a very generic CPU farm. All of our data reduction pipeline has FPGA in it. It has a card in it that has an FPGA. So we have the possibility to move things from either CPU or FPGA. We can always insert GPUs later, but until we get the detectors, the imaging detectors that need to operate at high rate, there's no point. So we're going to wait, because the longer you wait, the better you get. You know, there's this game of chicken that everyone always plays with GPUs. And so we are playing chicken just like everyone else. Yeah.
So how many processors?
How many processors do we have? In the data reduction pipeline, it is of order 80.
80?
80 right now to start operations. Ultimately, it'll be closer to 300. In the offline processing farm, how many is it right now? It's a good question. I should know this number because I just approved it. I don't have a good answer. I'll have to get back to you. I do have an answer, but I don't remember what it is.
Probably too few.
It's going to be at least 3 or 4 racks full, which are about 40 U, so 160 right now.
Yeah.
This is today's number. So in 4 years' time, we're going to take up half of the Stanford Research Compute Facility, the new one. So, it's going to end up being, 2 rows of 8 or something. So I guess 16 times 40. I'm going to take that as my back of the envelope calculation, because in terms of rack profile, that's what we were calculating.
So the other thing that's interesting is what sort of power requirements are these?
Yeah.
Because, Exascale computing, which is
Yeah.
sort of what you're nibbling at the edge at,
Yeah.
is sort of, it could take all of the power we can make plus then. Plus
Yeah.
some. You're gonna-
But they're already in the power business.
Yeah, in a sense, you're absolutely right. One of the reasons that we couldn't build a farm ourselves or put it in our standard compute facility is because there was not enough power or cooling to handle that. It was like 30 kilowatts per rack, so it's insane. So, but in the end, what we're doing is there is a Stanford Research Compute Facility at SLAC, which houses Sherlock. And this is a compute farm that's accessible to Stanford, for use. And we are currently using some spare racks in that room. So this is a bootstrap. This gets us started and gets us going. Someday they're going to expand that and build SRCF-II. And SRCF-II is a second building with presumably sufficient power, cooling, and a flywheel to maintain power through unexpected power outages, not that that would ever happen. And we will probably need approximately half of that new building. But it is expected, it's going to cost quite a lot of money, and thank you to Persis for allowing it to go forward. But it's going to cost quite a lot of money to build it, and that's going to be an enabling technology for us. It's going to give us a house for our offline processing farm, which we very badly need, because streaming data to NERSC sounds great and all, but they would scream so hard if we had to try to stream 100% of our data over there. We basically take up their entire cluster all the time because we're very bursty. It's very different from a simulation job.
So another number which I'd like to hear is what's the output in bits per second that the unit is going to be able to produce?
So the output in bits
And
per second.
What's the bandwidth you'd have to stream?
Oh, to NERSC or to
some remote?
ultimately a terabit per second?
Well, how many fibers you need?
Depends.
Is that continuous or burst when we get to
It's a burst. So it's 100 terabit per second for about 10-minute chunks, followed by 2 minutes of downtime, followed by another 10-minute chunk, at a terabit per second, followed by 2 hours of downtime because somebody is fiddling with something in the hutch, and followed by 2 hours of continuous running. So it's utterly random. And what was the second half of that question? There was a second
I
half.
lost a bit, I know that, I don't remember.
Okay. No, it's a terabit, and it's bursty, and that hurts NERSC. I know, it's difficult.
So, a couple of years ago, I was at a wonderful talk out at SLAC that pointed out that their support group was now so good that the grad students weren't doing that work anymore.
Yeah.
And there was a whole generation of grad students that weren't getting their hands dirty.
Okay.
Are you reinventing the role of the grad student? Are they going to be getting their hands dirty with data?
Yes, because the user is still writing their analysis on top of our stack. So the user is still the owner of the science domain knowledge. The trick is that you have to separate the computing required to do the analysis and the science knowledge required to go from raw data to introspection, to the ability to extract information and science from your data. And the students are still solidly in charge of that information extraction business, trying to get to the science and understand what this fit means, how it connects to this model or that model, why this blip is there. That is all solidly in the student's domain. All we do is provide the tools to visualize the data and to analyze it in a reasonable amount of time. So we do the computing work, which is a scaling exercise. It you need to understand computing architectures and how to write software so that it can parallelize and take advantage of whatever memory hierarchy you're living in. But it's an expertise that graduate students don't necessarily need, unless they're working with me, in which case you learn it, right, by doing it. So it depends. So there's computing, and then there's the science, and we're outgrowing the place where the scientists feel comfortable doing the computing. They haven't caught up to it. We're moving too far ahead.
Something I learned many years ago, and this is before PCs came out and people figured out that you had to compress your data and make it lossy so that you could fit the bandwidth
Yeah.
of the PC and things like that. I learned that, today you have GPUs and FPGAs and you have lots of compute power at your
Mhm.
disposal. If I threw a lot of compute power at medical imaging many years ago, a lot of compute power on it, I could get 100 to 1
Yeah.
lossless compression.
Yeah,
Lossless compression.
really?
Yeah,
Was it sparse, or was it because you were, okay,
Throw more horsepower at the front end
yeah,
so that you can get totally lossless compression, which reduces your bandwidth all through the pipe.
yeah,
And there's a whole lot of tricks like that you can learn.
yeah.
So it's
If you-
science.
If you think like that.
Right. No, and I completely agree. And we are trying to push as much forward as we can. We do have to cross a trust barrier, because up until now, the users have gotten all of the raw data, and they love every bit, right? And they want the raw data. I don't think they've been faced with
That's correct.
but I can't fit it on my laptop anymore, because they also want that ability to open their laptop and analyze, right?
That's correct. And because you did lossless compression,
Yeah,
have a little tiny pipe.
yeah,
And then they get it, and they throw.
They're
equal-
part of the small
They've
pipe.
got some more compute power to it, and they have all of their data.
yeah. Yeah, well, that is,
There's all sorts of tricks. You got to think like that.
yep,
There's a tradition in physics of taking data that was captured quite a long time ago,
Mhm.
maybe a week or two, and looking at that data and then finding new things in the data. When you do it this way, you don't have that as an option
No.
any longer.
you don't. You can only
And-
look at the pre-scaled data, the data that we leak through untouched, unreduced. That's the only place where you can look for it. And we're sensitive to that, because a user group did do that. They came in the first year, they did a very traditional experiment with nanocrystallography, and they found the Bragg peaks, and they found a structure, and they rejoiced and had champagne, and it was great. And then, some years later, they said, oh, hey, you know what? We can detect motion of these molecules and these proteins by looking at the diffuse diffraction in between the bright spots. So they were just looking at the bright spots and threw out everything else and did their analysis. But then they learned there was all this information in between those bright spots.
So I need the lossless data
And,
compression.
and so, yeah, lossless is great, and if we could do that generically for everything, we would. The problem is, it doesn't get enough of a reduction factor for all types of data. So I'm hoping that we get better and better at doing lossless compression so that,
Some of the astrophysicists have figured that out, but it's called mutual information, using information theory. Then you can do
okay,
the
okay.
lossless data compression.
Well, we'll look into it. I think the stuff that we've tried so far wasn't
The
enough.
guy just left, he went back to 1800.
Yes.
So are you saying they can detect the frequency of the vibration of the molecules?
They can see.
Better repeat the question.
Oh yeah, he asked if I'm saying that they can actually see the vibration of the molecules, and I think the answer is yes. I think in that case, I don't know that it was. I think what they were seeing. Yeah, I think they were seeing some dynamics in the system associated with bonds moving and things twisting.
So they are running at different frequencies,
Yeah.
and you are able to detect it accurately.
Lossless data compression.
Well, this was lossless. This was a raw data, and this was analysis on raw data. I'm not sure I have enough knowledge to be able to answer that concretely, but if you give me your email, I can send you a paper with a link to it.
So let me ask you this.
Yeah.
What is the maximum size of the target you can put in the system?
The maximum size can be anything that doesn't block the beam, so
So what happens to the target? Is going to
it usually gets vaporized.
be disintegrated? Is going to be
Yeah, you blow a hole in it.
Not within a live
Yeah.
animal there or something to image it.
No, although I've heard about fascinating experiences with spider silk at synchrotrons, which sounded like a wild experiment because I think they couldn't hurt the spiders, but they had to, and you have to stimulate the spider to get it to produce the silk because once it's dry, it's not. Anyhow, we've never done anything like that. No live animals. And there are certain ethical restrictions about what you can image. But I mean, you can certainly take the microchips, and there are methods for imaging things that are of order a few centimeters squared. And you take images right next to each other with some overlap, and then you reconstruct the image and look at what's inside. So there are various techniques that allow you to do that. Oh.
The first picture you have of the geography,
Mhm.
what happens in the 200 meters between the near?
There's
south
another
and
experiment
north
there
center?
called FACET. There's an accelerator experiment there. Back in the days when it was a high energy physics experiment, they needed the full 2-mile long accelerator to get the electrons and positrons up to speed so that they can get the right energy when they collide. But it was repurposed, and they didn't need that much runway in order to produce the X-rays, and so they only used the last third. And so the one part was FACET. That's a different experiment, a linear accelerator experiment at SLAC, and then the early part is going to turn into a new undulator for LCLS, or a new accelerator for LCLS that generates yet another beamline. So we're going to use that the most forward part of the linear accelerator to generate more X-rays for LCLS.
No, I'm looking at the other end, the experimental.
Oh, the experimental hall. Let's see if I can find it. Back to the pretty picture of the experimental hall. Yeah.
Yeah, the green blob there.
The green blob. Oh, the X-ray line, the XRT, the X-ray transport line.
Yeah.
Yeah, that's a fun one. I'm not sure what the provenance of that is. I've heard theories, so this is me hearsay, these are theories. I think when they designed it, they originally thought that maybe they might be able to put a mirror in at the near hall end to be able to put beam to end stations at various points across at the far hall, so they can go boom, 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 and feed multiple beam lines that way. And so they designed with that in mind, and then in the end decided it wasn't feasible or couldn't build it. And so we have this tunnel that doesn't really do anything. It just adds space. But yeah, I think that's the history, but don't quote me on it.
So, but there are several stations along there. Does the beam hit all stations?
Yeah, it goes through all of the hutches on its way down, but it only terminates in one. So yeah, as it goes, there are beam pipes. There's a soft X-ray beam pipe and a hard X-ray beam pipe. And you can be standing in the hutch that's closest to the accelerator and doing whatever you want, and the X-rays are going past you right there in the beam line. Right there, right past you. Just inside the beam pipe, which is totally cool. And it's only dangerous, really, once you get to the end, because, I mean, they're directed, they're photons. They go in the direction they go. They don't scatter much. And so they go in their direction, and then when they terminate and they actually hit the sample, that's when they become dangerous to human tissue. So you really only have to stay out of the hutch where the beam is ending up, but not along the path.
Same problem with the dental office.
Yeah, exactly. So the pipe's not the problem, but if, yeah, it's coming right.
Gamma ray,
Do I have a gamma ray?
gamma ray, after X-ray you have.
Yeah,
You can go
yeah.
much down.
I don't know, how high can this go? Up to 14.7 GeV. What is the cut? I don't remember where the transition between gamma, I mean, the 14.7 GeV is arguably gamma ray.
Yeah.
So it gets to gamma ray. Sorry, you had a question.
Yeah, so how many other free electron facilities are there around?
Yeah, so there's one in Japan called SLAC. There's the European XFEL and PSI,
ELI.
ELI
Yeah.
in I'm thinking of
That's
Switzerland.
one
The one in
thing.
the one
Yeah,
in
the Paul Schreber Institute,
yeah, the Paul Scherrer Institute. They have an X-ray laser.
Santa Barbara.
Santa Barbara?
And then Livermore decommissioned theirs.
Santa Barbara, probably yes. So there are synchrotrons in various places. There's the Advanced Light Source at Berkeley. These are rings. So they're slightly different means of production of X-rays, but they're still light sources. And there are 5 of them in the United States. There's the ALS at Berkeley, Advanced Light Source, Advanced Photon Source at Argonne in Illinois. There is NSLS-II at Brookhaven. There's SSRL, which is at Stanford, at SLAC, which is a smaller synchrotron at SLAC, and there's LCLS, and those are the U.S. ones. The free electron lasers, though, are a rarer breed. There are. I thought there were 2 in Europe, and one in Japan, but it's a growing field. Yes.
Have you done any single photon experiment?
Single photon, no. At least not with that. There are times when you try to get a monochromatic beam, so you get a particular wavelength, but you always want to have as many photons as you can. What sort of experiment were you thinking of?
Well, characterization of this atom by itself.
Ah, okay, characterization of the atom by itself. Yeah, I would say no. I mean, most of the time, I mean, when you have 10 to the 12th photons, only some fraction of those actually hit your sample and bounce off. So, you really are looking at a subset of photons, but it's very hard to find a single photon and direct it at the target. So I don't think we've done any of that. Are there
Excuse me.
any other questions? Okay,
Oh, what a great toy.
it's fun. It's pretty cool.